Hello, everyone. Good afternoon. Welcome to our AI seminar series. Today, we are here to listen to the talk named DeepLesion, Large-Scale Universal Lesion Analysis in Medical Imaging Based on Deep Learning. It's a great pleasure for me to introduce our speaker today, Ke Yan. And he is a senior medical algorithm expert in the Alibaba from China. He got his PhD degree from Tsinghua University. Then he worked as a postdoctoral in the National Institute of Health in the US. His current mainly focuses on medical image analysis using the machine learning, especially on lesion detection, classification, retrieval, and matching in CT images using deep learning. He has published many papers in the well-known journals and the conference such as CVPR in the areas of AI-based medical analysis. And now he has nearly 2,000 citations as a young researchers. Now, please welcome Ke Yan to give us the talk.
Okay, thank you, Kevin. Hello, everyone. I'm Ke Yan. So, as Kevin just introduced, I'm a algorithm expert or researcher in Alibaba DAMO Academy. So I have been working in the US for like 4.5 years, and I just came back from US and to China. So I heard that some of you are AI researchers, and I think many of you are familiar with certain fields of artificial intelligence, but I don't know how well do you know about medical imaging. So I will just show a medical image before I start my presentation. So as you see, this is a CT image. This is what I have been working on for like 5 years. This is a body CT image from the lung. This is this black field is the lung, and then you scroll down and to the liver, to the kidney, to the bowel, and finally to the pelvis. So this when you enter a hospital, sometimes they will give you like a CT scan, and the doctor will look at this image and tell you what kind of do you have any abnormality, do you have any lesions in the image, and they can also from this image they can tell you a lot of things. But as you know that in many areas in the world, the good doctors are very sparse. So when you live in a small city or in a rural area, you can't get a very good doctor to look at you as your CT scan or other medical images. Then you may get a misdiagnosis. And our goal is to train some deep learning models, and from the annotations of the medical experts, and build our algorithms so as our algorithm can be used in the less developed area and help them to get a better diagnosis, and also improve the quality of the medical procedure. So let's start. Lesion analysis is a big part of the radiologist's daily work. So when looking at the medical image, such as a CT, radiologists typically first will find the lesions in the image and measure them, how big they are, and describe them in the radiological report, and also maybe compare the lesions in this image with the other image of the same patient to see if the lesions have grown or changed. And since we want to build algorithms to help the doctors to improve their accuracy and speed, we also have some algorithms can do these tasks. For example, to find the lesions, we can build some detectors. To measure the lesions, we can train some segmentation algorithms, and also classifiers and retrieval algorithms. So these are our algorithms we can do to help the doctors. And there have been many researches on these tasks. However, they have certain limitations. Most of them only focus on certain body parts. For example, some of them focus on detecting lung nodules. Some of them detect breast nodules and liver tumors and brain lesion and so on. But in the daily work of a radiologist, they typically need to find all the lesions in all the organs in the image. So if we train one model for each organ, this is very inefficient. And also these algorithms require large annotation effort to annotate a small set of images. This is because medical images is very difficult to annotate compared to natural images, and it requires a lot of time and professional knowledge. To deal with these challenges, our goal is to first mine a large-scale lesion data from PACS. Well, PACS is a database of the hospital, and we want to do it with minimal human efforts. And we also want to explore a variety of lesions or universal. So we don't focus on only one or two organs. We want to analyze the lesions in as many as organs. And the third goal is to perform systematically and clinically important tasks, such as the detection, classification, matching, and so on, and eventually help in radiologists' daily work and improve their efficiency and accuracy. So this is the procedure. This is the flow chart of our plan. First, we need to do some data curation. We can mine the image and the annotation from the hospital system, or we can let the doctors to annotate some data. And then we can, from the image, we can train lesion detection algorithms to first find the abnormalities in the image. For example, these are two liver tumors. And we can also let the doctors to manually select the lesion in the image. For example, they can draw a box around the lesion. And in step 3, we can do a variety of tasks. For example, we can train a segmentation algorithm to accurately draw the boundary of the lesion. We can also directly train a measurement algorithm to measure the diameter of the lesion. We can also classify whether the lesion is a hemangioma or a tumor or a cyst, and what kind of attribute do they have, and what organ is the lesion in, and also we can match the lesion from the patient's first scan to the lesion in the second scan, so the doctors can conveniently compare these two lesions. And finally, we can also do lesion retrieval, which is we input one lesion image and we ask the model to find all the similar lesions in the hospital. So let me introduce them one by one. The first step is data curation. We collected a large-scale dataset called DeepLesion. This dataset is not collected by manual annotation. Instead, we do it by data mining. We first find the bookmarks stored in the hospital of NIH, the National Institute of Health. In NIH, the doctors, when they find a lesion, they will draw a bookmark such as a diameter to measure the lesion. And then this kind of annotation will be stored in the PACS. So we write some program to mine this kind of annotations, and we collected a large scale of annotations. Then we build a data set, and this data set contains over 4,000 patients and over 10,000 CT studies. One CT study is like when you go into a hospital, they will give you a scan, and this is called a CT study. And you know that a CT scan is a 3D image. It contains a lot of different layers of 2D images. So there are over 900,000 2D images, and there are over 30,000 lesion annotations. And these lesions have a big variety of size, from 0.2 millimeter to 300 millimeter. So we can see that the biggest characteristic of this data set is it is very diverse. So it contains all kinds of lesions. For example, these two are lesions in the lung. This is also in the lung, and this is in the breast. This is the liver, and so on. So this data set, we have published it in online. You can download it without any cost. This project has been working. So since I left, I entered NIH in 2017, and this kind of annotations have been collected since 2010. So there are more and more bookmarks collected in the NIH PACS system. So we can collect these annotations year after year. So it is very economical. We don't need any manual annotation. and it is universal, which means that it contains lesions in all kinds of organs. And we can, with these annotations, we can do some systematical tasks to help doctors. But it also have some challenges. For example, there are many lesion types, but in each lesion type, there are relatively limited data. And some lesions are very subtle, meaning that it looks very similar with normal organs. So if you are not an expert, you cannot classify whether this is a lesion or not. And also this dataset have imperfect labels, which means that not all the lesions are annotated in each image. We want to do some universal lesion analysis tasks. So why do we want to do a universal algorithm? This is because radiologists are responsible to find and report all possible abnormal findings in one image. And traditional single type models are unable to cover all kinds of lesions. So also with the universal lesion analysis algorithms, we can do some more in-depth analysis in our task, in our data. So the first task we do is lesion detection. This paper is published in Transactions on Medical Imaging. Our goal is to detect a variety of lesions in CT images. There are two possible applications of this algorithm. The first one is we can help lesion screening and triage. For example, in a very busy hospital, they may have hundreds of CT scans each day, and there are not so many doctors to look at all the CTs. So we want to use our algorithm to rank these CTs and find the lesions in these images. And if one image have many lesions, we can rank them to the top of the doctor's workload, so they can look at these images first. The second application is to reduce missing findings and to improve the sensitivity, especially for low-tier hospitals. For example, when a tumor patient comes, he may have a lot of lesions, and a doctor do not want to miss any lesion. So they may use our algorithm to help them avoid missing findings. I will just briefly introduce our algorithm, and if you are interested in it, you can take a look at our paper. So there are some key components of our algorithm. The first one is to mine the lesions and deal with the incomplete annotation problem. Incomplete annotation is a very common problem in medical images because doctors don't have time to annotate all the lesions in the image. So they may only this is for example, this is a 3D image with many 2D slices, and the doctor may only annotate one slice in the image, and we use a cross-slice box propagation to propagate this annotation to its neighboring slices and to complete this 3D annotation. And the second thing is that one patient may have several CT scans in our data. So in CT scan 1, the doctors may annotate 3 lesions, and in scan 2, the doctors may annotate some other lesions. And we want to use these 2 scans to complete the missing annotations. And to do this, we compute a lesion embedding for each annotation, and then we do an embedding matching to find the correspondence of each annotation in these 2 images. And then we can complete the missing annotations. And we also design a cross dataset lesion mining algorithm. For example, we can train our detector. We first train several detectors on different datasets. Then we use a model trained on dataset A to infer the images in dataset B, and then we can have some detections, and then we can keep those detections with high score, with high confidence as the uncertain findings. Maybe they are true lesions, maybe they are just false positives, and then we can use them as uncertain lesions and retrain the detector, and then ignore these high confidence detections, so that these missing annotations or false positives won't be harmful to the model training. So after these 3 lesion mining strategies, we can see that our average sensitivity improved from 36 to 46, almost 10% improvement. And we also find at first we have 20,000 ground truth annotation, and after this Lesion mining, we have 10,000 more. The second algorithm is multi-dataset learning. We have this DeepLesion dataset we collected. This dataset have many different types of lesions, but it also have some missing annotations, so that using it alone may not give us the best model. So we also get some other datasets. For example, Luna is a dataset for lung nodules, and this is a dataset for liver lesions, and also lymph nodes dataset. So we train our model on a combination of these datasets, and we train a multi-head detector. Each head is trained on one dataset, and then we fuse the results of these heads and to get the final prediction. This prediction can give us the better result because it contains knowledge of all these datasets. We call this model Lesion ensemble. It fuses knowledge from multiple datasets in feature and proposal levels. We can see this example. On the left is the green boxes are the detections of the DeepLesion head. We can see that it detects some large lesions, but it also misses some small lung nodules. These yellow boxes are also lung nodules, but missed by the DeepLesion head. And on the right is the Luna expert. The Luna is a lung nodule dataset. This head can detect all kinds of small lung nodules, but it missed this large one, which is have atypical appearance, but it can be detected by the DeepLesion expert. So by combining the output of these two experts, we can have the best sensitivity. So we also find that by joint training of multiple datasets, the sensitivity of the model can be improved on every test set. So we not only test on DeepLesion, we also test on Luna, on this, on NIH lymph node. So with the joint training strategy, the accuracy on each of these datasets can be improved. With this lesion detection algorithm, we also inferred some external test sets. For example, we collected some data from online data sets. We also collected some data from another hospital in Beijing. We got precision and recall about 60%. This is actually lesion detection in medical images is a difficult task, especially we want to detect lesions in all kinds of organs. So this result is not surprising, but it still needs to be improved. We find that relatively good accuracy can be found in larger organs such as lung, liver, lymph node, and so on. And we also managed to detect some small but critical lesions that may help the doctors to avoid missing findings. But we still have some problem. For example, vessels can sometimes be mistaken as lesions in non-contrast scans. For example, in this liver image, this too dark area is detected by the model, but actually they are vessels, not lesions. But you can see that in the training data set, this is also a dark area in the lesion. This is a true lesion. So you can see that the lesions in medical images are very, they have a lot of different appearance, and sometimes they can be subtle to detect. It is a very challenging task. There are also some false positives in the bowel and in some other areas. So these are the problems we are still working on to improve. The second task is lesion retrieval and matching, which we published in CVPR 2018. Lesion retrieval is the goal is to model the similarity between lesions, and then we can find similar lesions from different patients and help the doctors to understand the lesions. And we do it by learning deep lesion embedding on a large and diverse dataset with weak cues. This dataset is DeepLesion we just introduced. So in DeepLesion, we have some annotations such as the boxes, but we don't have annotations such as what type of lesion it is and what kind of attribute each lesion have. So we must learn the lesion attributes from some weak cues. So we first manually annotated 8 types, including the bone, mediastinum, lung, liver, kidney, abdomen, pelvis, and soft tissue. And then we train a classifier on these manual annotations and do lesion classification on all the DeepLesion data to get a coarse lesion type annotation. And next, we learn the relative body location of each lesion. We give a coordinate for each lesion. For example, this is a body. So this is a lesion. From the center to the left of the body, we have the relative x coordinate. And from this center to the top of the body, we can have the relative y coordinate. But the z coordinate is not trivial to have, because the z, as we can see from the this medical image, is, for example, this is a body. You look at this direction is the head, and this direction is a foot. So by z, we define the head as 0 and the foot as 1. So given a point, we want to know what z coordinate it is. For example, this may be point 3. But given 1, all of our data is on 2D slices. If you only give the model this 2D slice, the model don't know how long it is from the foot and from the head. So it don't know how to compute the z coordinate of this point on the image. Okay, so we further propose an unsupervised body part regression algorithm by spatially self-ordering the 2D slices. So although our model don't know which what slice or what z one slice is, but we know that in one CT volume, we have certain orders. For example, slice J is above slice J plus K, and this slice is above J plus 2K. So we have a natural order information of these 2D slices, and then we can randomly select this a series of 2D slices, and we input it into a convolutional network, and then we can predict one score for each 2D slice. And we ask these scores to form an order. We let S1 smaller than S2 and smaller than S3 and so on. We also let the distance of these two scores to be similar between each pair of the slices. And by optimizing these two loss function, we can let the network self-organize to learn the z coordinate of each 2D slice. And these are some examples. For example, this is the neck. We have the lowest score, and then we gradually go to the chest, go to the abdomen, and finally go to the pelvis. We can see that the score of this network output is gradually increasing. Note that we don't give the network any kind of manual supervision. We just let the network learn from this relationship of these scores by itself, and then it can self-organize to learn this score. And finally, after we have this XYZ, we have a third supervision cue is the lesion size, which is the long and the short diameter of the lesion. Then we can try to learn the lesion retrieval algorithm by using a triplet network with sequential sampling. We first randomly find a lesion, and this is called an anchor. Then we find another lesion in this DeepLesion dataset, which has a similar body part, a similar XYZ, and a similar size. And then we sample another lesion, which have a different size, but similar location and body part. And then we sample D, which have a different location. And finally, we sample E, which has a very different body part from all these 4 lesions. And then we can optimize this loss function by asking the distance between A and B to be the smallest, and then which is smaller than A and C, smaller than A and B. Finally, the A and E distance is the largest. And by optimizing this loss function, we can have a lesion embedding space, which we can hope to group all kind of small similar lesions together and push the different lesions apart. And these are some examples of our triplet which is used to train our network. And these are some examples of our learned embedding space. For example, these 3, the top left corner, are three lesions we sampled from this embedding space. They are they are close in the embedding space, and we can see that they are also close in the appearance. They are also in the similar body part, in the similar size, and also in the similar location. And next, we do a lesion classification algorithm, which is an oral paper in CVPR 2019. By lesion, in our previous task, we have grouped the similar lesions together, but we still don't know what kinds of lesions they are, what organ they are in, and what kind of attributes they have. So we want to give a prediction of the where, what, and how of each lesion. So we want to do some fine-grained semantic classification, and then these predictions can be used to generate structured reports to also collect some lesion data sets. For example, we want to find all the liver lesion in this data set. We can use this model to predict the organ of each lesion. And but note that we don't have these labels in the DeepLesion data set. So we have to do some label mining from radiological reports. This requires some NLP, some natural language processing. There are some related work which also mine labels from reports. For example, in this X-ray task, the researcher mined the disease label from the report. However, these are only image level labels, and in our task we want to find the lesion level labels, and we also want to find the relation of the labels. These are our novelty. So this is the framework of our algorithm. Given a lesion dataset, we first define an ontology of the lesion labels. For example, we have we have body parts, we have lesion types, and we also have lesion attributes. And then we further define some label relations, including the hierarchical and exclusive relations of each label. And then we designed an NLP algorithm to find the labels from the free text radiology reports. And then we have a text mining model to filter the labels and to only keep the correct labels and remove the noisy ones. And finally, with the knowledge from the label relation and this supervision from the labels, we can train a lesion annotation network to predict the lesion type, the body part, and the attribute of each lesion image. First, we define our radiology lexicon, which we find it in an online ontology called RedLex. In total, we defined 115 body part labels, 27 types, and 29 attributes. And we also defined some label relation. For example, the hierarchical relation is, for example, left lung belongs to lung. This is a hierarchical relation. And there are also some mutually exclusive relation. For example, left lung and right lung are mutually exclusive. So this is an example of the relationship graph of some lesion labels. For example, chest chest is a parent of lung and mediastinum, and lung and mediastinum, they are mutually exclusive. One lesion cannot be both in lung and in mediastinum, and so on. Next, we design an NLP algorithm. So given a sentence in the report, we have to find the relative labels of the lesion and remove those irrelative labels. And this is done by CNN and followed by some rule filters. And with the label relations and the mined lesion labels, we can do some label expansion to infer the missing parent labels. For example, this is a sentence, unchanged large nodule, for example, right lower lobe and the right middle lobe. And then we have our text mining model when we extract these filter labels, large nodule, right mid lung. And from the hierarchical label relations, we know that right mid lung belongs to right lung, belongs to lung, and belongs to chest. then these 3 labels are all correct, but they are not in the report. So we can infer these 3 labels and add them into our label set. This is the multi-scale, multi-label CNN structure, which is based on the VGG backbone. There are some special strategies we designed to train this network. One is called relational hard example mining. The motivation is that some labels are difficult to learn, and for example, one idea to learn these difficult labels is to use online hard example mining, but we know that these labels are extracted from free text reports, and the labels are incomplete. So when there are no such labels in the report, maybe this label is true, but if you want to make the network learn this label, it will give the noisy supervision to the network and harm the accuracy. So our idea is to use the mutually exclusive label relation to infer reliable negative labels. For example, in the report, we extracted the left lung as a label, and we want to train the network, but so we know that left lung is mutually exclusive to right lung, and if a lesion is in left lung, it must not be in right lung, and also not in liver, not in kidney, and so on. So these are reliable negative labels. We can give these labels to the network and then make the network to learn these negative labels. However, there are some unreliable negative labels, such as left lower lobe, such as nodule, and although these labels didn't exist in the report, they may be true. So we don't let the network to learn these unreliable negative labels. And this inference procedure is based on the exclusive label relations. And with this network and with this training strategy, we do our experiment on about 20,000 lesions with reports in the DeepLesion dataset. So these are some prediction examples. Given this lesion image, our network predict that this is a ground glass opacity, and then it is also nodule in the left lower lobe. And but there are also some false positive predictions, such as left upper lung and so on. So with this lesion, it predicts that it is a cavitary lesion on the right upper lobe. And these are 2 lesions in the liver. So our model can give some true positive predictions, and also maybe there are some false positive and false negative predictions. It can also perform lesion retrieval because it is trained on reports. It has better accuracy than our previous algorithm, which is trained on noisy and weak labels. For example, we input this image. It is a right rib lesion, and then we have this retrieved lesions. They are all in ribs, and there are also some mass, and with some calcification and some similar texture. So in summary, we try to mine data and label from existing databases and reports so as to get large-scale annotation with minimum manual effort. Sometimes manual labels are not available or too expensive to acquire. Then we can use some weak labels, some noisy labels, and do some self-supervision or unsupervised learning and so on to train our algorithm. And we also leverage expert knowledge such as the label ontology and label relation to improve our algorithm. And the next topic I want to introduce is anatomical point matching. This paper have been published in IEEE Transactions medical imaging. So the background is that radiologists often align and compare the same body part in different images. For example, they may have 2 images of the same patient, and doctor want to compare the same part of the 2 images. And so we want to train a model to train an algorithm to do this automatically. But if we want to train such an algorithm, we may need the doctor to help us to label some corresponding points in different images, which is very tedious. So we proposed a self-supervised algorithm. The motivation is that human organs have intrinsic patterns in radiological images. For example, all the patients have the lung, they have a liver under the lung, and they have kidney under the liver, and so on. So they have certain patterns in the body. An ideal algorithm should be able to discover these patterns from unlabeled images, so that given any point in one image, it should find its correspondence in other images without any supervision. So this is a mimic of human perception. For example, we have two images in this we have two images, and we have 2 points on the 2 images. In here and here, we can easily tell that these 2 points are correspondent, are similar body part, even if we are not doctors, but we can see that the appearance of these 2 points are similar. So we can hope that our algorithm can also learn this kind of similarity. So we formalize our task by generating an embedding on every image pixel in the image to encode its anatomical context information, so that similar body part in different images express similar embeddings, and it can be retrieved by simple nearest neighbor searching. This algorithm can be applied in many different occasions, such as lesion tracking, intelligent PECs, one-shot landmark detection, and maybe help other algorithms. Our algorithm is called self-supervised anatomical embedding, or SAM. It is based on the very hot topic called contrastive learning, which is a very hot topic in recent years. So first, we have a labeled medical image, a volume, a 3D volume, and then we randomly crop 2 patches in this labeled image and do some data augmentation to get 2 patches. And in these 2 patches, because they are both cropped from the same image, we know that these 2 points are corresponding. So we input these 2 patches into this 3D network and generate 2 embedding tensors, and we ask the embedding vector in these 2 points to be similar, and the embedding in other points are all different. So by optimizing this local and global info NZE loss, we can learn the anatomical embedding for each point. And this is the learned embeddings. So in the first row, we have a medical image. So we click 1 point on this point, and this is the top of the aorta arc, and we get a global embedding and a local embedding, and then we have another unlabeled image, and we also extract the global and the local embedding tensors, and we do a convolution operation with this point and with this tensor, and we get 2 similarity maps, and we can see that this point and this point have the highest similarity value. So by finding the maximum value on this point, we can have this point detected, which is exactly the point of the aortic arc of the top. And we can also have the third one image. This image is different because it has contrast agent injected into the vessel, so that the vessel is brighter. But our algorithm can still find the correct point. Our algorithm called SAM have many applications. So let me introduce some typical ones. The first one is landmark detection in CT. We can let the doctor click only once from a template image, and then our algorithm can find the corresponding landmark in all the other images. This is the right thyroid gland, and this is the bronchus. And we compared our algorithm, it's called SAM, with other image registration algorithms, and we can see that our algorithm have the smallest mean error, and we also are much faster than the traditional and the deep learning based registration algorithms. And this is oh, this cannot be played. Okay, this is the demo. I don't know why it cannot be played, so I just ignore it. And this is another example on X-ray. We can also detect landmarks on X-ray images by only one image as an example. And the third application is lesion matching in CT. So lesion matching is a very important task for doctors. Given one lesion in one CT scan, doctors want to find the same lesion in a second CT scan. So our algorithm can help the doctor to find the similar lesions. And we do an experiment on 1,000 lesion pairs, and our accuracy is over 90%. And our algorithm can also help to improve CT image registration algorithms. We can find a grid on one CT image and use SAM to find the corresponding grid on another image, and then we can compute a transformation matrix to transform the one image into another to best align these two images. This paper was published in last year's MICCAI. And we can also use our algorithm to do some medical image classification. In summary, our proposed algorithm SAM map every pixel in radiological images to a semantic space, and it can be used to find the corresponding anatomical points. When training, it uses only unlabeled images, and it is very easy to implement. And in inference, it only needs one labeled image, and it is also very fast and robust to different variations in CT images. And it has wide applications and potential usages. And it also has some limitations. For example, if one image have no texture in one area, our algorithm may not perform well because it cannot find the features to match. And when two images have very large deformation, it may also fail to detect the correct point. But the traditional algorithms may also fail in such cases. Our last topic is lesion segmentation and measurement, which is mainly done by my colleague named Yubao Tang. So lesion measurement is also an important task for radiologists because they will need to measure the lesion size to know that how severe the lesion is and what stage the patient is in. But manual measurement of lesion size is very time-consuming and requires professional knowledge, and also often are subjective and prone to inconsistency. So Dr. Tang proposed several algorithms to automatically measure the lesions. This is the method he proposed. He input one CT slice and also a point clicked by the doctor, and then the output of the network is the segmentation mask and the lesion diameter measurement of the lesion, which the doctor have clicked on. So the algorithm is UNet-like architecture, including a encoder and a decoder, and he also input some prior knowledge into the encoder, and also with some scale-aware attention in the decoder to improve the accuracy of the segmentation algorithm. And let me see if this okay. Maybe I don't have the source videos in this slides, so it cannot be played. Okay, that's all. Thank you.
Thank you. For any any persons, do you have any questions? Maybe I think you can just ask, and Co will help us to answer this one. Okay, maybe I can ask one question. I think this talk is quite good, and it covered many aspects of the medical image analysis, and also the method used quite common. It can be used for many other fields in the computer vision. And I think I'm particularly interested about the self-supervised part. I think you mentioned that you used this one when you do the I think let's say I think it's like page 20 or something. Page 20, and I think you mentioned this kind of scan, they are just ranked in some order, and then you are trying to use the self-supervised learning and to get some better performance, right? Yeah, it's here.
Yes.
So can I ask what is the, here you see there are some orders. What is the difference between different order? What is the order, the dimensions is time or something?
Oh, the order is ranked by the Z coordinate. So the city is a 3D scan. So you can see that this is the x-axis, this is the y-axis, and this is the z-axis. We have one 2D image in each of the z coordinate. So it is from the head to the top to the foot. This is the z order.
So it means the height of the person, like a different height level. Okay, that's very great. And also, I think you mentioned in the first paper, you mentioned in the talk, I think you also use some method to propagate the labels from one frame to other frame. I think it's the first paper you mentioned. I don't remember. Yeah, this one. Yeah. I think here in the figures part A, you mentioned that there's just one frame that is labeled, but you use a method to propagate the labels to other frames. Can you explain how we do that one?
Oh, actually, it's quite intuitive. So we first train a detector from the existing labels, from these incomplete labels, and then we run the detector in all the frames or other slices, and then we have some detections. And then we compute the intersection over union of the boxes in neighboring slices. If it is larger than, for example, 0.5, we will group the neighboring slices, the boxes in the neighboring slices, and then we can propagate the boxes.
So is this similar to some pseudo label?
Yes, it is.
Okay, so you use pseudo labels and also use the IOUs to eliminate some kind of false positive and then get the result.
Yeah, I use the detections as a pseudo labels, and then we find if the detection is overlapping with existing annotation, we consider this detection is a true detection, and then we add it into the detection set, into the label set, and which are the neighboring slices.
And also, I see there's a question from the QA. And it means how do you envision in the close future the interactions between medical imaging specialists and the ML assisted diagnosing techniques? Do you think machine learning will keep assisting those experts, or one day it will completely replace them?
That's a very interesting question. Several years ago, I remember that Hinton said that the algorithms will someday replace the doctors, but I don't. But this time has passed. The algorithms is still far from doctors actually. So I don't think one day they will replace human doctors. But nowadays, doctors do use algorithms a lot. They are the algorithms are intensively helping doctors. For example, in lung nodule detection. Many doctors don't know how to detect lung nodules without the help of AI algorithms now. This is just kidding. They still know, but the algorithms are helping them a lot, and they save the doctors a lot of time, and also find many nodules that they may miss if they look at the image by their own. So and there are more and more such cases. For example, in the eye, there are there are some algorithms which can help doctors to find the diseases in the in your eye, and also in your breast and in your brain and so on. So I think there will be more and more algorithms in like entering the radiologist daily work. But as you know, I am a researcher in the company. So as a company researcher, I think we will not let the algorithm take the full responsibility, because one day if it make a mistake, maybe the patient will sue us, and they will say that it's your fault. And so we will always make the doctors to make the decision. We just help them. We tell them maybe this is maybe that is normal, but the doctors are always in charge.
I see. I think in your slide, I think basically most of them says not about how to diagnose based on this kind of AI method. It's just to help the doctor to get them to get some conclusion, but the conclusion is just from the doctors, not from the machine.
Yeah.
And
so
also there's you go.
Oh, okay. Sorry. So the tasks we are focusing on is to help the doctors to perform something that it is very tedious to do by themselves. For example, lesion detection. If there are many lesions, it may be very time consuming. So we'll help them find them, and we also help them to measure them. And this is a measure a lesion, maybe not very hard for doctors, but it is time consuming. So we help them to do this, and also help them to match the same lesions. So, but for diagnosis, it is a very it is a harder task. So it may include many prior knowledge. For example, if you only look at one image, it is hard to do an accurate diagnosis. You need to look at different kind of scans, including CT, including MR, X-ray, and you have to also look at the patient's symptoms, look at the patient's blood test, look at their even gene tests, and you can finally make an accurate diagnosis. So this is what we're not doing now, because maybe we'll do it later.
And also there's another question from Rux, and the question is, have any of these algorithms been practically deployed or tested in hospitals? And when in the future do you expect for it to become routines for hospitals to use deep learning algorithms, and what are the challenges? And finally, imaging machines like the CT or MRI can come from different vendors. So can this impact the algorithm performance?
Oh, there are many questions. Okay.
Yeah, the first one is about have any of these algorithms been practically deployed or tested in the hospitals?
Sure. We in one slide we introduced our results in an external hospital in Beijing. So we train our algorithm in from data in NIH in the US, and then we test our algorithm in data in hospital in Beijing. So the accuracy is not perfect, but it is kind of like give us some hope. We also lesion. This is because lesion detection, especially for universal lesion detection, is very challenging. But we have also some other algorithms which have been success. For example, our lesion tracking algorithm, we have deployed it in another hospital in Shanghai, and the doctors are happy with it. And for the lesion measurement algorithm, it is also very already mature and accurate. So we also deployed it in a hospital in Shanghai. So the second question. What is the second question?
The second question is, when in the future do you expect for it to become routines for hospitals to use deep learning algorithms, and what is the possible challenges?
Oh, I think they have been a routine in many hospitals. just as I said just now, like the non-audio detection algorithms. And I think there are several cases, but the most famous one is non-audio detection. And there are certain challenges. The one challenge is your third question, because there are some different city vendors, different city, like there are also got different parameters and different patients, and there could be some domain gap between different images. So if you train your model on one hospital and test it on another, it may be there may be some accuracy drop. So you need to adapt it to different hospitals and different data. Actually, this is one problem I'm trying to address now. So one solution is to train your algorithm on many hospitals and many data. So data is the is a driving force for deep learning, you know. And if you collect more diverse data from different hospitals, different data source, you can train a more robust model. And the second one is then you can deploy your model to a hospital and let the doctors to try it, and they will find some bad cases, and maybe this is because their data is different from your data, and then you can adjust your model to adapt to their data. But in my experiments, if you can train on sufficiently large and diverse data and do some data augmentation and try to avoid overfitting, it can perform relatively well on new data. This is because CT images, although there are some variation, but it is not very big. So the CT image all have some, for example, in this image, the values, the pixel values have certain physical meanings. For example, water is always 0, and air is always like a -1000. And different CT scans, different CT machines will always give you similar values for similar material or similar tissues. So the domain gap is not very challenging problem.
Okay. Okay, let's see. I think there's no other questions from the QA. Okay. So I have one more question, and I think you just mentioned that you have mainly developed the method and they have been deployed and tested in the hospital. Can I ask you how large of the data size you use to train this kind of model?
The lesion detection model I just mentioned is trained on the DeepLesion dataset and 3 different datasets. Let me find okay, here it is. So the DeepLesion dataset contains over 10,000 patients, over 10,000 images. This is not a large number for natural image, but it is a large one for medical image. And for the other 3 datasets, it typically contains like 100 to 1,000 images. So in total, there are maybe over 10,000 images to train our algorithm. And for other models, they are also trained on DeepLesion. So the data scale is similar.
Okay, I see. And also there another common question. I think there for our audience, there are some students that are just a graduate, they are fresh graduate, and also there are some PhD students that are going to study their PhDs during TII. And maybe I think can you give him some advice or suggestions about how we can have some successful careers, especially in the AI field? Because I think you are one of them.
Yeah, thank you. Yeah, I think many of you have many good experience and good advice. I don't know if my advice can be applied to everybody. I think the first one is to choose a good topic. There are some topics you may spend a lot of time, but you may maybe it is not a good topic, and you may waste a lot of time. But I don't think you have to choose a very hard topic that everybody is working on. That will be very competitive. And the best thing is to talk with more experienced people. For example, if you want to do medical image, you can talk to many researchers in this field, and also talk to doctors to see what their problems are, and you can combine their problem with your knowledge to see which problem can be solved by your knowledge, and then maybe you can find a good topic. For example, the DeepLesion project is defined by my supervisor in NIH, Dr. Summers and Dr. Lu. They see that there are many. They find such an opportunity that were not explored before. They find that there are a lot of data and labels stored in the hospital's database, but none of them have been used by AI algorithms. So they asked me to mine them and to build algorithms based on them. And this is I think this is a successful case. So, but without the Dr. Summers is a radiologist, and Dr. Lu is like a computer specialist. So they when they combine their knowledge together, they discuss with each other. They come up with this idea to leverage this medical data with AI knowledge. So sometimes if you discuss with more people, you can find such opportunities which maybe not haven't been tried by anybody before, and this will be your opportunity. And the next thing is to I think is to make a good use of your time. So when you do your PhD, is your golden time. So because when you go to work, even if you go, even if you enter like an institute or a company which focus on research, you will have a lot of different things to work on. Maybe you don't have a whole time to do the research. So in PhD, it is the best time to do what you're interested in, and also to I think artificial intelligence in many occasions can be compared or can be mimicked with like human intelligence. For example, you can make use of your prior knowledge into your algorithm. For example, in my case, I just noticed that like the images in one city volume are in order. This is a prior knowledge, and then I incorporate this prior knowledge into our algorithm, and then we can train a body part supervisor with no annotation. So such prior knowledge or such intuition is very important. It can always give you some novel idea and make the reviewers say, "Wow, this idea is very genius. It is so simple, but it works so well." So such, I think this will be very valuable. Yeah, that's some of my comments.
Yeah, I think that are very insightful suggestions, and also I think maybe there's no other questions. And thank you very much for the excellent presentation, and I'm very pleasured to have you today. So maybe we can just have you again in some futures. Maybe you can just give us more talks about these other topics.
Yeah, thank you.
Thank you very much.